a string. So now this is vertical, and so this is going to go around with angular velocity omega, and we have a string here, and the string is attached to this ball, and the whole thing is going around, and so at one moment in time, this has a velocity, like so, and therefore there must be non-negotiable centripetal acceleration, which in magnitude is omega square r, or if you want to, v squared divided by r. Now, I cut it, and that's like taking away the push and the pull. The string that you have here is providing the pull on this ball. This ball is feeling a pull from the string, and that provides it with the centripetal acceleration. Cut the string, and the pull is gone, and the object will take off. And if there were gravity here, as there is in 26,100, it would become a parabola, and it would end up here. If, however, I cut the ball exactly when it is here, not the ball, but I cut the string, then of course it would fly straight up. Gravity would act on it, would come to a halt, and it would come back. So really would then go along a straight line. But you would clearly see then that it's not going to do what many people think, that it would start to swirl around. It just goes and comes back. Let's look at that. We have that here. So here is that ball. The string is behind here. You cannot see the string. I will rotate it. Wait for it to pick up a little speed. And the knife that you can't see either is behind here. And when I push the knife in, I do it exactly here. It cuts the string and it goes up. You ready for this? You sure you're ready? 3, 2, 1, 0. Wow! That was very high. So you see, it's nothing like this. It simply continued on in the direction that it was going. It wasn't going into a parabola because I was shooting it straight up. The string forms the connection between the rotating disk and the ball, and therefore the pull is responsible for the centripetal acceleration. Let's now think about planets. Planets go around the sun. There's no string. So who is pushing? Who is pulling? Well, it's clear that it must be gravity. It must be the sun that is pulling on the planets. Now I realize that the orbits of planets are not nicely circular, so it's not really a uniform circular motion. We will deal with orbits in great detail in a few weeks, circular orbits and elliptical orbits. Let us just assume for simplicity now that the orbits are roughly circular, just to get a little bit of feeling for it. And you can look up now in your book, which I did for you, even in your preliminary version, you can look up what the mean distance of the planets is to the sun, and you can look up what the period is, the time to go around the sun. The time to go around the sun is not the same for all planets. The planets are not attached to a turntable. Anywhere, any person on a turntable would go around in the same amount of time. We know that that's not true for planets. It takes the Earth a year to go around. The Sun, it takes Jupiter 12 years to go around. So don't make the mistake to think that omega is the same for all planets. That's not true. So I look up the distance, the mean distance to these various planets, and you see that here in millions of kilometers. Notice that Mercury is about 100 times closer than Pluto. By the way, this is on the web, so don't copy this. You will find this on the 801 homepage. Then I looked up how many years it takes to go around the Sun. 12 years for Jupiter, 1 year for the Earth, and I looked up all the other values. Then, since I know the periods, I can calculate omega. Omega is 2 pi divided by t, so I know omega. And then I take omega squared times the mean distance to the Sun, and this is, of course, the centripetal acceleration. So the planets experience this centripetal acceleration in some crazy units, but who cares about the units here? And notice that Mercury, which is 100 times closer than Pluto, has a centripetal acceleration which is 10,000 times larger than Pluto. 100 times closer, has a 10,000 times larger centripetal acceleration. So what I did was, I plotted this data, the centripetal acceleration versus the mean distance to the sun, and I did that on log paper. And what immediately is very striking is that all these points, I've done them for all the planets, they fall on a straight line. And so, what is the slope of that line? Well, I tried various slopes, and I found that the slope is very, very close to -2. Here is a slope of -2, and I can overlay this and notice that the fit is absolutely stunning. Therefore, you cannot escape the conclusion that the centripetal acceleration, which is the result of gravity, falls off as 1 over r squared. We refer to this often in physics as the 1 over r square law, and therefore the effect of gravity itself must go down with r squared. So if you are 100 times further away, like Pluto compared to Mercury, then the centripetal acceleration, which is due to gravity, is 10,000 times smaller. And we will learn a lot about gravity in the future. We will just leave it for now. If you took the sun away, it would be like cutting the string that provides the pull, and in that case, what you would see is that the planets would just take off along a straight line. They would continue to go. They wouldn't have anything to pull on them anymore. Now, let's look at an object that we are going to rotate. I have a glass tube that I want to rotate, and in the glass tube I have a marble. The glass tube is very smooth. I have here the glass tube. Here is a marble. I'm going to rotate it in this direction, say with some angular velocity omega, about an axis perpendicular to the blackboard. So the marble here has a velocity, like so at this moment in time, but it's a very smooth glass tube. And the marble is very smooth. The glass cannot push on the marble, nor can the glass pull on the marble. Now the marble gets desperate because the marble needs a centripetal acceleration in this direction in order to go around like this. But there is nothing to provide that centripetal acceleration. So the marble is doing exactly the same that the planets would do. If you take the sun away, the marble continues to go in the direction that it was going. So by the time that the tube is here, the marble is here. And by the time that the tube is here, the marble is there. So the marble finds its way to the edge. And that's, of course, the basic idea behind a centrifuge. My grandmother had always, she was a great lady, and she had such fantastic ideas, I remember. And when she made lettuce, we had no good way of drying the lettuce. And I would take the lettuce and go like this, paper towel. She had a method of her own. She took a colander. And of course, first of all, we would wash the lettuce. That goes without saying. I would wash it once. My grandmother would wash it 3 times. But that's what you have grandmothers for. So there comes the lettuce. We were also very fond of spinach. So add some spinach. We would wash it. There goes the spinach. then she would